I've selected a problem out of chapter 6. Now that chapter is having to do with entropy and cycles and thermal efficiency, coefficient of performance, determining if certain cycles are possible or impossible. I've selected this problem because on the surface, to me, it looked very difficult, very involved. And then the more I studied on the given information, I discovered that the problem is extraordinarily easy. And so I thought might use this as an illustrative example of things that might appear to be very difficult, but turn out to be easy. And that's a good example of a classic quiz or test problem. So let's get started. Problem 622, and here, this is a sketch of problem 622, and then we'll look at the problem statement here. Okay, it says figure P622, shown there, provides a TS, temperature entropy diagram, of a Carnot refrigeration cycle for which the substance is R, refrigerant R134A. And you're asked to determine the coefficient of performance. And so on the screenshot, so that to me, when I started undertaking this problem, I thought, oh no, this is going to be a tough problem. I'd better allow a lot of time because I see a cycle. Although it's a Carnot cycle, there's 4 processes. I'm asked to find the coefficient of performance. I think I'm going to have to analyze every process, determine the network, determine the energy sought, which would be the heat transfer QL. And then I started studying on this. So notice here, so let's look at, so looks tough, but it turns out that it's really very easy after a little studying. And so notice here on my slide, I put an exclamation point recognizing that this given information in the problem statement is golden. It's critical. Carnot refrigeration cycle. So that's a classic cycle. It's the best you can possibly do. It's the best performance you can get operating under certain conditions. I look at the sketch and then I nod my head. Yes, I see the Carnot cycle is a rectangle on the temperature entropy diagram. All that fits. Okay, that's making sense. What else do I see? I see I've got refrigerant and I see that there's a vapor dome drawn on my sketch. I look at it and I say, well, okay, it's rectangular. It's some of the cycle is under the dome. Some of the cycle is up in the superheated vapor region. So I see all that and I start head scratching. So let's move on to the next thing. If you need a refresher on cycles and thermodynamic cycles in general, in other words, what's the coefficient of performance all about? What's the definition of coefficient of performance for a power cycle? What's the definition of thermal efficiency? I'd like to chase you to my playlist, Thermodynamics Cycles. And if you can find Carnot Cycle 101, that's going to really help you quickly. I see it's 54 minutes. It's going to help you refresh your memory on cycles in general, but then really learn quickly about what's special about the Carnot cycle and why is it the best you can possibly do in terms of performance. A little commercial for Carnot cycle 101. All right, let's go back for our problem in general and let's understand what's given in the sketch. And so I'll have to disclose, I started studying this thing. Those text boxes kind of represent the thoughts that were in my mind about what I was looking at. I do observe that at state 2 for this Carnot cycle, we're a saturated vapor there, and then we're going up reversible adiabatic to state 3, and at least I observed that the refrigerant is at a pressure of 16 bar. So that's going to be, let's see, well, 16 bar, good enough. It's superheated vapor. The phase of state 3 is superheated vapor. I'm coming over back under the dome to a saturated liquid condition. I see that T3 equals T4, and that's going to be TH, isn't it? That's T high. reversible adiabatic down to state 1, which is under the dome. This is going to be a nightmare. Am I going to have to find the quality at state 1? Oh my gosh, this is going to be tough to determine the coefficient of performance. So those little text boxes represent what was going through my mind when I was planning my work. And then it took me a while. And so I kept, for the sketch, I kept harping on this 16 bar thing. And finally, out of the corner of my eye, I noticed this label over here, 0. So that says that this temperature down here, process 1 to 2, isothermal reversible expansion, is occurring at a temperature of 0 degrees C or 273 degrees K. So, I said, look, T1 equals T2. That's a given number, and it also equals TH. And so then I started saying, okay, I think I'm getting it. Let's see, what do I know about the Carnot cycle? And with the given information, how can I proceed? This is a classic quiz or test problem because the professor or instructor is thinking, well, I'm going to let this is an easy problem. However, a student who's doesn't know a lot about the Carnot cycle has the potential for spending a huge amount of time in a test or quiz crunching numbers, trying to get things, and not really realizing the fundamentals. And so heads up, this is a good example of an easy quiz or test problem, but the pitfall is if you're not familiar with the Carnot cycle, you end up running the risk of spending spinning your wheels and wasting a huge amount of time in a timed situation. So let's move ahead. What do we recall about the basics of a Carnot cycle? And the best thing to do to refresh our memories of what we know about a Carnot cycle is to draw the basic schematic diagram of any system operating in a cycle. Here's our black box. Here is our block arrow going in a counterclockwise direction to show that it's a refrigeration cycle. That's given in the problem. Refrigeration cycle. What we're doing in a refrigeration cycle is we're transferring heat from a cold space by way of QL up into the cycle, and then we're transferring heat up to a hot reservoir, TH, and what we have to invest is we have to invest a certain amount of work. So W out net is less than 0. We've got to invest work to make that happen in the real world. Okay, so what's the visualization of this schematic? The visualization for a refrigerator is recognizing that TL, that's the cold space. It's like the cold space in your refrigerator. Cold, inside the refrigerator. And so the objective of a refrigeration cycle, is to transfer heat from the inside of your refrigerator to the surroundings, to your kitchen. And you realize that you've got to invest some power. You've got to plug your refrigerator into the wall to get electric power to run your refrigerator. That's the crash course. That's the basics of any refrigeration cycle. Okay, now back to Carnot. Well, for any refrigeration cycle, the coefficient of performance is QL over W net. That's true for any refrigeration cycle, Carnot or irreversible. We apply the first law. We say, wait a minute, a little more. It's QL, the denominator, W net. Well, by the first law for a cycle, that's just QH minus QL. Okay, got it. QH minus QL is W net for any cycle. All right. Now we drop down to what we know about the Carnot cycle. The best performance you can get from a refrigeration cycle. I remember from class, all the way back to my student days, for a Carnot cycle, QH over QL exactly equals TH over TL. That is an identity. It can be shown, it can be derived for reversible, fully reversible cycle like the Carnot cycle. But I remember this, QH minus QL is TH over TL. And so in terms of a shortcut, I can replace Q's with T's in the coefficient of performance expression. So COP for a refrigerator for the Carnot cycle, I've got TL over TH minus TL. So what was given in our problem? TL was given as 273 degrees K. Well, it's really given as 0 degrees C, but we know to immediately transform that into absolute temperature. TL is given. Okay, wow. It remains to determine, okay, so we're asked to find this coefficient of performance. We don't know TL, so all we have to do is find TH. By hook or crook, if we can find TH, we've got the numerical result for Carnot coefficient of performance. Okay, let's see how we do that. How do we find TH? Do you see how easy this is? Okay, here's the gift. Back to the problem statement. I've put a big wrapped package on the gift, and there is the gift right there. TL was given, okay? Now, okay, and so how are we going to get TH? How do we get this temperature right here? How do we get that? Do you see how we're going to get that? Let's look at the details of how we're going to get TH, or T3 equals T4. How do we get that? All right. So let's draw down what we know. And so I've got to move my zoom image here. Here's a little thumbnail view of our sketch, our basic sketch. And let's study on it. And for what's given, how can we find T3? So that's the key. So as we're studying, one thing we know about process 2 to 3. So this is the easiest way, okay? We study on process 2 to 3. Do you see that state 2 is a saturated vapor? And you know the temperature of T3. Okay. So you could look up S2. I said 3. Pardon me. It's 2. I have to look. I'm craning my eyes to see that that's a state 2. S3 equals S2. So if we can look up S2 somehow, we know a value for S3 because process 2 to 3 is isentropic. That's a key understanding in thermo. Process 2 to 3, isentropic, reversible adiabatic. Okay. Also given in the problem, so I've got S3. If I can get S2, I've got S3. I'm also given that P3 is 16 bar. Pressure is known. Wow. That's 2 independent properties at state 3. 2 properties at state 3. Okay. If we can get T3, we've got TH. Okay. And then we've got it made. It's plug and chug for the coefficient of performance. Okay. We've got 2 independent properties. If we can find S2, okay, that's easy. We're just going to go to the temperature table and write down S sub G, aren't we? State 2, saturated vapor. We'll write it down. Okay, then we're going to go, we visually see the phase of state 3, superheated vapor. We will go to the superheated vapor refrigerant tables. We'll find 16 bar. We're going to shop around for the correct S value, and we probably will interpolate to find T3. And then we're basically done. Get it? Okay. Look how easy that is if you know the fundamentals. All right, so here we go. We will look up S2 using the temperature table for the refrigerant. We've now got 2, that's step 1. Step 2, we recognize that S3 equals S2. Now we've got 2 independent properties, S3 and P3. We'll use that to determine T3, and that equals TH. And we use our Carnot coefficient of performance for a refrigerator expression that we've got in our head to determine the coefficient of performance. Okay, now we can start putting pencil to paper and start writing numbers down. We've planned our work. All right, let me move my zoom. We're going to go to our refrigerant 134A temperature table. That's given. We're going to look up 0 degrees C. We recognize that the phase of state 2 is saturated vapor. So we're simply going to write down the entropy of the saturated vapor. Here's our saturated vapor entropy, 0.919. We write that down in our solution with units, kilojoules per kilogram degree K. Next thing we do, we're going to go to the superheated vapor tables. State 3 phase is superheated vapor. We go to 16 bar. We start shopping for a number 0.919. Uh-oh. Here's my choices. I don't see 0.919, but I do see 0.907 and I see 0.946. My number is in between those. So these two numbers are straddling my number. That means my temperature 60 and 70 degrees C is straddling my number. Okay. Now let's say this is a quiz and let's say you're running short on time. It took me a while to think about this, but I think I got it. I'm there. What would you do in a quiz situation to maximize your partial credit? You would write on your solution, my S value is in between 60 and 70 degrees C. So I don't have time to do the interpolation. I'm just going to pick a number between 60 and 70. I'll pick 65 and I'll calculate the coefficient of performance using 65. I'm kind of writing this down on my solution, making it clear that I know my temperature is not 65, but I'm explaining I don't have time to do the interpolation. Fortunately, here we've got the time. So I set up a little interpolation table, okay, with my given information. My entropy is 0.919. And so in Excel or on your calculator, you can quickly determine that T3 is 63.12. It's in between 60 and 70. My guess of 65 wasn't the best, was it? That was just a guess. It's a number in between 60 and 70 if I'm running short on time. But look, if I've got time to do the interpolation, my temperature is 63.12. I've got to turn that into absolute temperature. So I got 336.12. I am home for, that's TH. I am home free. Coefficient of performance that I remember from my head, TL over TH minus TL. Very quick calculator study to see that the coefficient of performance for this problem is 4.33 coefficient of performance for a Carnot cycle. And there it is. So didn't this turn out to be an easy problem? Looked tough. What did we learn from working through this? Well, one was we were given a sketch, but we had to study that sketch. We didn't even have to make any other sketches. It helped me to draw that schematic of the refrigeration cycle. That helped me out to kind of pin together, I need TL and I need TH for the Carnot cycle. All I need is TH and TL. That's what prompted me to sort of out of the corner of my eye, see that TL was given as 0 degrees C. You've got to understand the fundamentals. Start with the fundamentals before crunching numbers. Blindly using formulas is a loser. So do you see that for this problem, you could get mired down in lots of time-wasting work if all you did was depend on detailed formulas. Okay, and so then the last part is understand the power of the Carnot cycle. So simply the word Carnot refrigeration cycle in the problem statement, that's what really delivered us to the promised land. So those are all keys associated with this, what turned out to be a very easy problem. Okay, I hope that helps you get through a problem like this. I also hope that it helps you mentally prepare for taking quizzes and tests, right? Because that's where your performance is evaluated in this class. Little of your performance is evaluated in your turning in homeworks, getting grades for your homeworks. I think you're figuring out if you turn just about anything in, you're going to get a pretty good grade. If you just turn in some attempt at a solution, you're going to get a decent homework grade. But your overall performance in this class is going to strongly, strongly depend on the way you're evaluated on your performance in quizzes, tests, and the final exam. So be thinking about how can I learn the fundamentals in order to improve and maximize my performance on tests and quizzes. So hope that helps, and hope to see you in some of these worked out problem solutions.